So myself, Varad Daoo, I am a doctoral student at the Department of Chemical Engineering, IIT Kanpur. Right. So in the last class, what we have done, we have seen about the quantum mechanical nature. Right. Then we have studied about the Schrodinger equation for hydrogen atom and how this quantum mechanical model is able to explain the atomic spectra of hydrogen atom, the different atomic spectra. Right. Then we also further understood the important features of quantum mechanical model of atom. And then at the end, we studied about the concept of orbit and orbital and difference between them. And then we established that there are three principal quantum numbers which arises out of the Schrodinger wave equation, which could characterize the position of an electron. So these quantum numbers are the principal quantum number, the azimuthal quantum number, and the magnetic quantum number, right? So we are going to study in detail about these quantum numbers, okay, in this class. Lecture 30, structure of atom. The first topic which we are going to study is quantum numbers. So what are quantum numbers? So as discussed earlier, the orbitals represent the region in space around the nucleus where the probability of finding the electron is maximum. A large number of electron orbitals are possible in atoms. These can be distinguished by their size, shape, and orientation. To describe each electron in an atom in different orbitals, we need a set of three known numbers, right? So these are called as quantum numbers, and these are designated, right? So let us write this down. To describe each electron in an atom in different orbitals, we need a set of three numbers known as quantum numbers, right? And these are designated as these are these quantum numbers are designated as L, L, and ML, right? So this is the principal quantum number. This is the azimuthal quantum number, right? And this is known as the magnetic quantum number. So we are going to study in detail about all this. So in addition to these three quantum numbers, a quantum number is also needed which specifies the spin of an electron, and that is called as spin quantum number, right? So this is also right there. In addition to these three quantum, so these three are the principal quantum numbers, right? These three, which are very important. Another quantum number is also required, which specifies the spin of an electron. Specifies the spin of an electron, and that is called as spin quantum number, and it is denoted as mg. So there are in totality how many? Four quantum numbers, out of which three are primary, yeah, which are very important, and fourth one is just denotes the spin of electron, right? So let us study the first one, which is principal quantum number. Right? So principal quantum number determines the main energy shell or level in which electron is present, right? So it determines the main energy shell or level in which the electron is present. Electron is present and is denoted by and is denoted by N. So this is basically N can be 1, 2, 3, 4, or similarly it can also go in alphanumeric way, alphabetic way, K, L, M, N. Right? The principal quantum number also helps to determine the average distance of electron from the nucleus, right? So each electron will be defined. So there can be many electrons in one shell, right? So with the set of these four quantum numbers, each and every electron can be precisely denoted, right? So it's a encoding system for to identify each electron. These four quantum numbers will do that, right? So principal quantum number also helps to determine the average distance of an electron from the nucleus. Right? For example, if n is equal to 1, that is first shell, it is closest to the nucleus and has the lowest energy. Closest to the nucleus and has lowest energy. As the value of n increases, as the value, so this symbol denotes increases, the distance of an electron from the nucleus of an electron from nucleus increases. Right? Nucleus also increases, and also the energy of an electron in that shell increases. Right? Thus, what we can say is principal quantum number gives the average size or average distance of the electron from the nucleus and energy associated with it. Right? Now we'll move on to the second quantum number, which is azimuthal quantum number. Azimuthal quantum number, it is also denoted as L. Right? So this quantum number determines the angular momentum of an electron. This quantum number is also known as orbital angular momentum or subsidiary quantum number, right? And it is noted by the symbol L, right? The value of L gives the subshell or sublevel in a principal energy level cell to which an electron belongs, right? It can have positive integer values ranging from 0 to n minus 1. So let me write this down. So this quantum number determines the angular momentum of an electron, and this quantum number is also known as orbital angular momentum subsidiary quantum number, right? And this quantum number is denoted by this letter L, and the value of L gives the value of L gives the subshell or sublevel in a given principal energy state, right? In a given principal energy state, right? This is very important. So there are subshells present inside the main energy level, right? And that is denoted by this, right? It can have positive integer value ranging from 0 to n minus 1, right? Where n is what? N is the principal quantum number, which we studied in the previous class, right? Where n is the principal quantum number. Right? That means L can be 0, 1, 2, up to n minus 1, right? For example, for n equal to 1, L is only one value, that is 0, right? For n is equals to 0, L can have 0 and 1 value. For n is equal to 2, we can have 3 values, right? Which is 0, 1, 2, right? Thus, for each value of n, there are n possible values. There are n possible values of L, right? So in other words, the number of subshells in a principal shell is equal to the value of n, right? And these are called as so there is a special one is the numerical representation of this, and there is also another definition of which is in letter form. So let us understand this. So what we have is value of L and designation. So let's say if we have a value of 0, we call it as S, and this is a small letter, right? 1, then we call P, 2, then we call D. If this is value of 3, we call it F. 4 is there, then we designate it as G. 5 is there, then H, and then so on and so forth, right? So this is the numeric representation for L, right? And this is the alphabetic representation of L, right? The letters S, P, D, and F originate from the terms sharp, principal, diffuse, and fundamental, which were used in atomic emission spectra, right? Let us write this down. The letters S, P, D, F originate from the terms sharp, principal, diffuse, and fundamental, right? Which were used in atomic emission spectra. Which were used in atomic emission spectra, right? The different subshells or sublevels are represented by first setting the value of n and the later designation for the value of L, right? Let us write that down. The different subshells are represented by first writing the value of n, right? And then the latest designation, and then the later designation for the value of L, which is nothing but S, P, D, F, like this, right? For example, for example, an orbital with n equal to 1 and L equal to 0 is denoted as 1s, right? Right. Similarly, an orbital with n equal to 3 and L equal to 2 is denoted as 3d, right? Why? Because we know from this that for a value of for L equal to 2, the value of letter representation of L is nothing but D, right? Hence we are having D here, right? Right. Now the designation, right, of subshells for N equal to 1 to N equal to 4 are given below, right? So there is a table of this. Okay, the value of N, the value of L, subshell designation, number of subshells in a shell. What we have is N equal to 1. So allowed value of L is only 1, that is 0, right? And it is called as 1s. So 1. So there is nothing called as 1, 1D or 1P, because the allowed value of L for N is equal to 1 is only 0, right? So now if we consider, let us draw. Okay. Now we have N equal to 2, right? The allowed value of L will be 0 and 1. So 0, 1 we call as 2s. This is 2p, right? Club together we have here 2. Right? So there is nothing called as 2D or 2F, right? Okay. So similarly, now we'll move on to the next one, which is 3. So allowed value for this will be 0, 1, and 2. So let us draw like this, right? And these values will be we are 3s, 3D, 3. Sorry, this is 3, this 3p, and 3D, right? And total are 3, right? Now we have 4. So allowed value will be 0, 1, 2, and 3. So this will be 4s, 4p, 4d, 4f. Club together we have 4. So for third orbital there is nothing called as 3f. For second orbital there is nothing called as 2d or 2p, 2d or 2f, right? And in the first orbital there is nothing called as 1s. So there is nothing called as 1p or 1d or 1f, like this, right? This is very important. Right? So except for hydrogen, the subshells within a given shell differ slightly in energy, right? The energy of a subshell increases with increasing value of L. This means that within a given shell, the subshell with L equal to 0 has the lowest energy. The subshell with L equal to 1 has this next to lowest, followed by D and F and so on, right? So order will be, I will mention it, right? So let us write this down. So except for hydrogen, the subshells within a given shell differ slightly in energy, right? Slightly in energy, and the energy of a subshell increases with increasing value of L, right? So this means that within a given shell with L equal to 0 has the lowest energy, then P subshell with L equal to 1 has next to lowest energy, so on and so forth, right? Okay, so for N equal to 4, let us write this down. The energy will be 4s will be lowest in energy, followed by 4p, then 4d, then 4f, right? And this is increasing order of energy, right? Thus what we can say, thus angular quantum number, or also called as azimuthal quantum number, determines the subshell in a given principal shell energy shell, right? So this is very important. Then a sub right, and then a subtopic which we are going to study is angular moment of electron in an orbital, right? This is also related to the azimuthal quantum number, hence we are going to study it now. Of the electron in an orbital, right? So the angular quantum number gives the energy of electron due to the angular momentum of the electron, and the angular quantum number of the electron is related to L, right? The angular quantum number, which is nothing but azimuthal number, azimuthal quantum number, gives the energy of the electron due to angular momentum of the electron, right? Of the electron, and angular momentum is related as angular momentum is nothing but h by 2 pi into square root of L into L plus 1, right? This is also written as h cross into L into L plus 1, where h cross is nothing but h by 2 pi. This is a standard nomenclature which we use for h by 2 pi. We write it as h cross, and is h with a dash over the h over the h symbol, and it is called as h bar, right? H cross. The third quantum number which we are going to study is angular magnetic quantum number, right? The third topic is magnetic quantum number. Magnetic quantum number, and is denoted by Mn, right? So this quantum number describes the behavior of electron in a magnetic field, and we know that the movement of electrical charges is always associated with magnetic field, right? So this quantum number associated with the behavior of electron behavior of an electron in a magnetic field, right? Since the revolving electron possesses angular momentum, it will give rise to a very small magnetic field which will interact with the external magnetic field of the earth, right? So under the under the influence of external magnetic field, the electrons in a given subshell orient themselves in a certain preferred regions of the space around the nucleus, and these are called as orbitals, right? Under the influence of external magnetic field, which is, for example, Earth's magnetic field, the electrons, right? The electrons interact with so under the influence of external magnetic field, the electrons in a given subshell orient themselves in a certain preferred region, orient themselves in a particular in a preferred region, not a particular, but in a preferred region of space, right? And around the nucleus. These are called as orbitals, right? Thus, this quantum number gives the number of orbitals in a given subshell. Right? Thus, this quantum number gives the number of orbitals in a given subshell, right? And is denoted by, for a given value of L, M can have values from minus L to plus L, right? For a given value of ML, given value of L, M can have values or ML can have values minus L to plus L, including 0, right? That is, ML can have values minus L, 0, L, right? For example, in other words, what we can say is, there are 12 plus 1 values of ML for each value of L, for each value of L, right? For example, if L equal to 0, M has only one value, that is ML is equal to 0. That is, S subshell has only one orbital called as 2s. Sorry, 1s, right? Called the S orbital, right? If L is equal to 1, ML may be minus 1, 0, or 1. That is, P subshell contains 3 orbitals, right? 3 orbitals called as P orbitals, right? And these are indicated by numeric. These are indicated as, let us say, P plus 1, P0, P minus 1, or Px, Py, and Pz. If they would have been, right? So let us draw the table. So we'll do it on the next tab. So in this table, what we will have is value of N, then value of L, then values of Mn, then subshell, right? Number of subshells. Last step would be number of orbitals. Now we'll write for n value of 1, Possible values of L is 0. Then possible values of ML would be what? 0. Subshell will be 1s. Sorry. This will be 0, right? This will also be 0. The subshell is 1s. Number of subshells will be 1 and number of order bytes will also be 1. Then we'll move on to the next, which is 2. So for 2 we have L value of 0 and 1. This is 0. This is minus 1, 0, 1, or should we say plus 1? Your orbitals will be 2, subshells will be 2s to p. This is 1, this is 3, and in totality it will be 4. Right? This is how we'll continue. For third, we have, let us use red color. So for n is equal to 3, we have possible values of L as 0, 1, 2. This is 0, minus 1. Then here it will be 0, then plus 1. Here minus 2, minus 1, 0, plus 1, plus 2, right? This is called as 3s, 3p, 3d. We have 1, 3, 5, and in total it is going to be 9, right? So totality is going to be so like this, and then it's going to be like this, right? Right. So next is the number of orbitals in a given subshell are named like this, right? So the number of orbitals in a given subshell are, let's say this is subshell, this is number of orbitals, right? It's going to be s. For s is going to be 1, for p it's going to be 3, for d is going to be 5, for f is going to be 7, so on and so forth, right? Thus magnetic quantum number, what does it do? Thus magnetic quantum number determines the number of orbitals present in a given subshell. Determines the number of orbitals present in a given subshell. Now we are going to study the last quantum number, which is the spin quantum number, which is denoted by ms. Don't confuse this with ml. Right? So it is observed that the electron in an atom is not always revolving around the nucleus, but is also spinning around its own axis. So in 1925, George and Samuel proposed the fourth quantum number known as electron spin quantum number, and this number describes the spin orientation of the electron. It is designated by ms, and since the electron can spin only in two ways, that is clockwise or anti-clockwise, and therefore the spin quantum number can only take two values, which is plus half and minus half. This quantum number has a value independent of the values of other three quantum numbers. Instead of giving the number ms equal to plus half or minus half, the two orientation could also be explained by by arrow way of understanding it, right? Right. So let us write this down. Electron in an atom is not only revolving around the nucleus, but also around its own axis, much like the earth, right? To denote this, a new quantum number was proposed, or a fourth quantum number. New quantum number was proposed, right, in 1925 by George and Samuel. This is called as the spin quantum number, and it is denoted by ml, and it has a value of plus half or minus half, or it can also be represented by this arrow notification. Right? This quantum number is independent of other quantum numbers, right? Right. So in order to understand this, let me grab a picture. Right. This would be the pictorial representation. Right. So this is the anti-clockwise speed, and this is the clockwise speed, and the possible orientations of spin of electron is plus half and minus. Right. Then the next point is, does an electron has also spin angular momentum, commonly known as spin, and the magnitude of the spin angular momentum of an electron is given by this expression. So spin angular momentum is given by square root of s into s plus 1 multiplied by h by 2 pi, or we can also write this s into s plus 1 multiplied by h cross, right? Because we know h cross is nothing but h by 2 pi, right? For example, for a value of s equal to plus 1 by 2, the spin angular momentum is going to be square root of 1 by 2 multiplied by 1 by 2 plus 1 into h by 2 pi, right? Which corresponds to root 3 by 4 h by pi, right? So to sum up the summary of quantum numbers. So the first point is going to be, to sum up the four quantum numbers, they provide the following information about the orbitals. The principal quantum number, or n, determines the shell, which determines the size of the orbital, and also the large extent the energy of an orbital. So n describes the shell, which determines the size of the orbital, and also to a large extent the energy of the orbital. To a large extent the energy of the orbital, right? L, that is the azimuthal quantum number, determines the subshell and the shape of the orbital. So if there are n subshells in nth shell, right? There are n subshells in nth shell. To some extent, L also determines the energy of the orbital in a multi-electron atom, right? So L determines the subshell and shape of the orbital, right? There are n subshells in nth shell, right? To some extent, L also determines the energy of the orbital in a multi-electron atom, of the orbital in a multi-electron atom, right? The third point is going to be, the magnetic quantum number determines the designates the orientation of the orbital, right? So ML describes the orientation of the orbitals, right? For a given value for a given value of L, ML can have 2L plus 1 values or number of orbitals. For example, 1s orbital is L equal to 0, 3p orbitals for L equal to 1, and so on and so forth. The fourth point is MS refers to the orientation of the spin of the electron, right? So these are the nutshell. So points which are to be highlighted are like this, right? Orientation and orbitals, right? Thus, what we can say is thus the four quantum numbers describe the position of an electron. The position of an electron in an atom by specifying its mention, which is nothing but n, the subshell within the mention, which is nothing but L, the orientation of the orbital, which is nothing but the ME value, right? And the direction value, ML value, and the direction of its spin, which is nothing but MS. In other words, this quantum number serve as an address for an electron, right? So in other words, this quantum number serves as the unique address for an electron. Thus, the quantum number introduces the concept of shell, subshells, and orbitals, and the values permitted, right? So let us drag down. Thus, the quantum numbers introduce the concept of shells, subshells, and orbitals, right? So let us draw a table, symbol, information provided, and permitted values. The first is principal quantum number, which has a symbol of n, which gives the information about shell, and its permitted values are like this. Then is the azimuthal. L, it gives you information about subshell, and its values are 0, 1, 2, up to and -1. The third is magnetic, with the value of ml. It gives information about orbital, and it has a value of -l, 0 to +l. The last is spin quantum number, designated as ms, gives the information about spin, and permitted values are plus of or minus of. Okay, so in this class, in this lecture, what we have seen the different number of different types of quantum numbers which arises through the Schrodinger wave formulation of Schrodinger wave equation, and we saw that each quantum number is significant in its own way and provides some particular information about the electron present inside the atom. With the help of all these four quantum numbers, we can exactly address or exactly pinpoint the electrons, and hence these four quantum number act as a identification for the electrons, right, present inside the atom, right. So in the next class, what we are going to study about, we are going to study about the Pauli's exclusion principle, right, which states that no two electrons in an atom can have the same value for all the four quantum numbers, right. That is precisely that should be intuitive from our discussion till now, because set of four quantum number uniquely should be able to uniquely define or describe the atom, right. And then further, then we will study about the shapes of the different orbitals. We will briefly go into that, and then at the end we'll study about the electronic configuration of an atom, and then different principles such as Pauli's exclusion principle, Aufbau principle, then like this enhanced rule of maximum multiplicity, right. So that will be the last lecture.